Uh, okay, so we talked about this game previous time, if you remember. It was this game that is called PBeauty. If I write it correctly. So, what is the idea here? We had this essentially gameplay. The people are selecting a number between 0 to 100. And then a person will win the game if he is p times closest to the to p times the average. Good. This was the game. So, and we played with different p. So one time was p equal to 1, and I think the average was something around 43 or 45. It was 47. 47, yeah, actually. It was very close to the essentially average of number. Then we played another time and say that p is equal to 3 over 2. And average was something around 90, I think 5 or something like this. 90 something. Good. So, and lots of people were 100. So this is actually that's the thing that is important things here. The connection between game theory and social behavior. This is it. You can see this game. You see, this is just some simple number between 0 and 100. But you can actually play this game in a repeated things. So we are doing one time, let's do it again. Like instead of 2/3, we could get it instead of 3 over 2, we have it 2/3. It can be 1 greater than 1 or less than. Good. This is a very philosophical game, actually. How come? So you can just think about it, and then you will see how this very simple game, as I mentioned, and but there are even some competitions on that. Some people say that if you run this game one time, that says the average intelligence of the community of that. So if you run this game for the first time for a community, the number that you will get it can indicate the intelligence of that community. Even there are some studies like that. So that's you see, that's exactly the beauty of game theory. You will see a simple game, but it has very far-reaching, essentially, conclusion you can get out of this, and there are studies of that. Even for Prisoner's Dilemma or other famous games that we talk here. So here, what is the idea? The idea is that, say, if we had 3 over 2, say if we had it p equal to 2 over 3. You can see what is the equilibrium, especially if it's a repeated game. The equilibrium for this game is that everyone goes 0. Good. So what is the idea? You see, just think about it. The people all try to, now I want to say from the, essentially, social behavior of the people, essentially. Think about this. You have essentially a country. There are, say, two, essentially, parties, Democrats and Republican, or any other parties, right or left. What will happen? So when I put it p equal to 1, is that you want to be on the average of this. But generally, to get attention, especially in social media, etc., if you are average person, you don't get that much attention. What will happen? You want, the person who is working on social media, they want to get attention. That's the whole idea of essentially social media. To get attention, if you are, for example, say Democrat is 0, Republican 1, or vice versa, doesn't matter. So then if you are a Democrat or you are left, for example, you want to be a little bit more left than others. That is exactly the concept of p is less than 1. So for p, anything p less than 1, the equilibrium actually would be 0. What's the meaning of that? And this is a repeated game. The people are playing every day, essentially, towards an election, for example. You want to get more attention. you need to be a little bit more left than others. This is exactly this game that is doing. You will see near, very close to the election, the people are almost zero, completely to the left. Unless there is some essentially event that changes, I don't know, a war or something like this. The same thing also for that. If for the people who want to be a bit right than others, then to get the attention, you need to be a little bit more right. And this is a repeated game. So at the end of the day, the parties actually go quite to the right. So this you can actually, if you understand this game, and as I mentioned, Nash equilibrium, you can say that if p is less than 1, essentially 0, and if p is greater than 1, then that would be essentially 100 here. And if it's p equal to 1, the stable thing would be the 50 essentially. So you can think about this game and the equilibrium of this game. And with this game, actually, you can describe lots of real world things that is happening. And again, this, I'm not so sure it is written somewhere. These are some of my more thinking that I have done it over the years, essentially, on these games. And this shows that, I mean, like a particular game, the same thing about Prisoner Dilemma. These are like philosophical games. And when it becomes repeated, it becomes harder. And then you need to think about how can we get the equilibrium, etc. But that has, you will understand the whole world better. Yeah.
But in the election example, like in election, if a left wing is competing against a right wing,
yeah,
wouldn't have a situation where like half of people have a p less than 1, half of people have a p greater than 1.
Yeah.
So like the average would be around 1.
Yes, so that's another question. So this game that I mentioned, it can describe maybe in a more short-term thing, essentially, some behavior. So you can think about like in a, maybe that the whole election is just too far, essentially, for this game. So you can think about in a short term that some event happens, you want to be essentially a little bit more left than others. All of a sudden, it becomes shift quite a bit to the left or to the right. But the election, it might be the case for different people have a different objective. So at the end of the day, like if everything is calm, maybe at that time, then p equal to 1/2 makes more sense essentially. And of course, so this p can change during the game as well. But this one that you have mentioned in the short term, it can describe it. Then you can add more complexity to that and understand the situation. Does it make sense? That's the essentially beauty of, I mean, this is called PBeautyGame, and you can read more about it essentially. And there are some papers on that and others, but these are some of my thinking as well. But that's the thing that if you think about it, game theory actually, even with some simple numbers, but then it gives you much more understanding about the whole world. I say why the people become at some event happens, some people try to become very left, some people become right. But again, this p can be reset during some time. And then again, p equal to 1/2, something happens, then that the same thing happens. Great. So that's the thing that I wanted to finish from the previous time when we have played the game. This was the conclusion that I wanted to mention. Let me go and to this session. Okay, so so far we talk about normal form games. We have seen some of the tools for game theory, probability theory, and linear programming, and we understood something about the game. We played some game in the class, and also we learned how we can formulate it using normal forms. And that was the start. The previous one that we talked about is PBeautyGame, that how you can analyze and understand it and understand what is the equilibrium or the essentially some kind of a stable case. Now we want to go and understand more about it and see what are the concepts that exist for this game. Good. So, so uh, again, some remembering of the previous things. Uh, we consider two strategies in normal form games. One is the our pure strategies. Pure strategies are just a single action that these guys that or girls are taking. Mixed strategy is is probability distribution over pure strategies or all actions. And as we discussed, that is talking about some randomization over the actions that you can take. And as I mentioned again, the randomization generally comes from the history. So you may think that these normal form games are somehow limited. For example, somebody said that if the temperature is greater than 70, then I will do this action, otherwise I will do that. So that it seems that maybe it is not here, but actually you can also, lots of them still you can formulate it by adding more actions to this and make it. So the size of the table goes up, but still you can formulate these games. So it seems here it's restrictive, but indeed you can actually consider it more general. And as I mentioned, the general idea, if you want to uh, somehow formulate any complicated game, is that you should consider all possible scenarios or all possible actions that a person can take it as like a pure strategy. Generally, then the size of the matrix goes up, but you can actually analyze these games, or at least represent them as a normal games. There might be some correlation, etc., that's a little bit more complicated, but there are some concepts for that. So it seems restricted, but it's not that restricted. It's a very nice form of the game. And we will see more examples of this in the future, but uh, one other thing, by the way, we talk in this class about a book. You said we are talking about the chapter of the book. For example, here, chapter 3 of the book. Here, the main book, we have two books essentially: Algorithmic Game Theory book and Essentials of Game Theory by Kevin Litton Brown. That's the one that we are talking more. It is like a short thing that talking about it. We have much more materials here, but when we refer to that, if you want to see as a book, that's the book that you can also read from it. But we are talking and going above and beyond the book. But there is some other examples or others if you want to see, you can see from. So when there is like you can see lots of optimization problems. Optimization problems are indeed like single agents decision games. So if there is that's the thing that we talk about game theory versus uh, essentially or algorithmic game theory versus regular algorithm design. In algorithm design, you try to optimize something, and everything else is something that you have a control. In the algorithmic game theory, no, you can still you try to optimize the thing, but you don't have the full control. There are some other players. So if there is single agent case, it means that there is just some algorithm to optimize something, then you are finding generally an optimal strategy. And again, this is the whole idea of like, for example, P versus NP and finding a polynomial time algorithm solves the problem, find the optimization problem. So we cannot always find the most efficient way there, but at least we know what we are looking for. When there are multiple solutions, then that concept even does not work. Because then what's the meaning of optimum solution? Optimum solution only can mean for one particular person, like especially in, say, zero-sum games. Your loss would be my win and my loss would be your win. So in that case, it does not make any sense to talk about the optimum solution, unless if we want to talk about one person. However, that's the thing that we will talk about best response instances, and we will talk about it. However, even that is not enough, because if I do something, this is my current optimum solution, but you may decide that this optimum solution, I get like essentially a cake cutting problem, I get a good part of the cake, so maybe I could get better cake. You change your action. I need to change my action. The question is that, can we reach to some settlement again, some equilibrium? So that's the thing that it is called, essentially, we are talking about the solution concepts. So what are the solutions for the game is that what are the equilibrium of this game by some definition, or what are the stable case, what are the settlement case for the things that the people are somehow happy by some definition of happiness. You may define essentially some kind of fairness or other things that, like, for example, this concept of envy-free that we may talk later in this course, or other things that you are defining it, and of course the concept of Nash equilibrium and this Pareto optimality. So here, in this case, we are talking about two important things: Pareto optimality and Nash equilibrium. And then we go from there. These are two important concepts. There are more that we will talk later, but these are like some good ones, and especially very general ones. And here, also another interesting thing. So far, we talk about, I mean, lots of the tools, and we have some definitions, but not everything is about definition. Now we are going to the math, and you will see quite a bit of math involved, essentially, and probability involved, such that we can analyze this, because we cannot analyze this just by talking. That's the part that, when the math part or the computational part comes into the play, and makes the things much more challenging and interesting. Pareto optimality. This is the first concept that we want to say. So again, whenever we talk about a strategy, means a strategy that one person takes, and it can be pure or it can be mixed. A strategy profile means vectors of all agents involved. Good. S1, S2 to Sn, say n player game. Now, a strategy profile, which is a vector, S, Pareto dominates another strategy profile, S prime, if we have these two conditions. No agent gets a worse payoff with S than with S prime. Again, here, whenever we talk about the payoff, we mean expected utility. Good. And we have defined the expected utility before. That when you consider the expected utility, you need to consider this kind of normal form matrix or array. See what is the probability that the people land in a particular cell. And in that case, what is the probability times the utility that you will get? Sum it over all cells. That would be your expected utility. So payoff, if it is randomized, if S is mixed, it means expected utility. Otherwise, it would be the payoff that you will get it as a pure. Then you will go for pure. Then you can just read it from the one cell of the thing. So no agent gets a worse payoff with S than with S prime. It means that the utility I, and again, utility I means utility I or expected utility of S is greater than expected utility of I in S prime for all I. And not only that, at least one agent gets a better payoff with S than S prime. So for one agent I, we have strictly this was greater than or equal. Here it is strict. So a strategy profile S is a Pareto optimal or Pareto efficient if there is no strategy profile S prime that dominates or that Pareto dominates S. So what is the whole idea? The whole idea is that if there is something, it means that you can think more like, for example, in the collaborative games or common payoff or like some of these non-zero sum games even. So there is one place, like one strategy that like this is S. There is another S prime that in every aspect is better than S. For everyone is better, and even for one person actually is completely better. Why these people should stay at S anymore? They can go to S prime, it's better for everyone. At least for one person, it gets a better. So it's a very reasonable thing. Now, what is the concept of Pareto optimal? Pareto optimal or Pareto efficient is that we reach a S that there is no other S prime that can dominate it. Okay, this is not the best thing, but at least we know that you cannot. So at least we reach a place somehow on the boundary. It means that if I change it, at least for one person gets worse. That's the whole idea. So that's about this. Is the definition clear? Yes. A strategy profile is essentially a vector of strategies of each person. Like this S essentially, S means S is equal to S1, S2, and Sn. These are the strategies that, and we are talking about simultaneous game, essentially, simultaneous action.
So strategy is how they pick the profile.
Yes. And again, each of them, it can be a randomized one. So you can also see the slides and the previous lectures. We will talk exactly about this. So this is, each of them is a random, it can be a randomized one, or it can be pure, just one action. And this is a strategy profile. This is S is a strategy profile. Good, that we can take it. Now, so that's the meaning of that, essentially Pareto optimal or Pareto efficient. But no one can dominate this. Now we want to go to the proof. The first claim, and this is now the math is coming to the play, and probability theory. Every game has at least one Pareto optimal profile. Not only that, always at least one Pareto optimal profile in which all strategies are pure. So these guys are not randomized, are not mixed. These are pure strategies. Good. Here, before going to the proof, I want to give some essentially example that this may seem actually easy, but that's somehow intuitions of all this. This is the question. Is it possible that a person, I mean, say, all the grades that he or she gets it in a class is at most A, but her GPA or his GPA becomes A+. Is it possible? Okay, so let me change this one. So the numbers between 0 and 100. Is it possible that all your number grades that you get it in different class, and the GPA is the simple average, it is like below 60, but your GPA becomes 70? That is not possible. That's very important, actually. This is the non-trivial things. You may ask some people, they may, at the beginning, it may not be that trivial to them. The same thing, is it possible that all grades that I get it are greater than 50, but my GPA becomes 45? The minimum would be 50. So that's the concept that I'm using here in the utility function. And this is, again, seems simple, but you can try this one. Talk with some people who are not that mathy, and you will ask them, and they say, oh, yeah, why not? I mean, it can be possible. I mean, but you can. That's an important one. But you will see actually it's become even non-trivial when we are discussing here. So let's see the proof. So here I'm telling two ways that you can do it. One of them would remain for exercise. I want to give, so that is the thing. So I want to produce something. And both of them here, we are talking about the pure strategies. Because I want to say there is a pure one. You don't need to go to the mixed one. You can create mixed one as well, but this is a pure one. So if we can, generally, if we can obtain something with pure, it might be easier because there is no mix and the things would be easier, but not always this exists. Good. So how can we do that? Let's consider for now for 2 agents. You can do it for more than 2 agents. We will find a pure strategy profile with the highest payoff P for agent 1. Good. So let me just draw this one.
Is taking the strategies of other players into account, right?
Yes, of course. So this was let me draw this one. So I think it was 3-3. What was that? 5-0, 0-5, and then it was 1-1. Correct? That was, say, for example, say prisoner dilemma, if I have written it correctly. I just want to give you the idea. Okay. So you will go and you will find, so I want to find the pure strategy profile. What's the meaning of pure strategy profile? It means that I can just focus on, I want to, like each of these guys, these cells in the normal form game is indeed a strategy profile. It's a pure strategy profile. Because this guy takes C, this guy takes D, this is a strategy profile, pure strategy profile, and then we will end up here. So in some sense, each cell in this normal form game is indeed a strategy profile, pure strategy. So among them, I need to report one of them, which is Pareto or Pareto efficient. Good. I will go among all these ones, among all pure strategy profiles means going to this table, find the one that has the highest for the first person. For example, here, for the first person, this would be the one that has the highest. Good.
And the second person would choose D and then return 1.
Which person? No, I will continue that. Let me finish this. So yeah, so among everyone, you will go the one that has the first player. This is say first player, has the maximum. Then among all pure strategy profile, for which agent 1 has the payoff P, so here it has the 5. So P would be 5. The highest payoff would be P max, essentially would be high. P1 max. For player 1, the maximum would be 5, so this is 1. Among all of them, I will go and find the cell that has the maximum for the second player. So this would be, among them, would be P2 max. In this case, P2 max would be only there is one that has 5, so it would be 0. the third player, I will go among all that they have 5 and 0, find the one that has the maximum for the third player. Good? And so on and so forth. And if there is, so in that case, it might be if just this is the only one. So if there is nothing, if there are even more than 2 players, this would be the one that I want to choose. Good. Is it clear? The algorithm? The algorithm this is the one that you should be able to write the code essentially for that. You will go there, you will find among all the cells, the one that has the first player, the maximum payoff. Among all those cells that have this maximum payoff, you will find the one that has the second player has the maximum payoff. Among all them, you will find the one that has the third the maximum. And you will continue until the thing that you are finding, ending up with the one cell always. Maybe more than one, but you can choose at that time only one, the last one. Yeah.
You do the same thing for starting with players.
Yeah, you can do it with any ordering of players. You can.
But you will get a different answer.
You may get a different answer. Here we will say that there is at least one Pareto optimal. There might be lots of Pareto optimal. Again, this is not a complete solution. This is just one solution in the sense that this is you want to reach a state. It is not a stupid solution in some sense. And here, by a stupid solution means that if there is some other strategy profile that everyone can get a better things, or at least the same, and one person can get better, why not go to that strategy? That's the only thing that we are talking about. We want to find a strategy that there is no one that dominates it. Good. And this is the algorithm, as I mentioned. You can take any ordering of the players, call it player 1, 2, 3, and then go according to this one and this algorithm. I want to say that this strategy that you end up is a Pareto optimal or Pareto efficient. Good. Now, before going through that, one important thing that I want to emphasize is that, okay, we need to say this one, that there is no one dominates it. No one dominates it not only among pure strategies, but also among mixed strategies. That's the one that makes a little bit the proof more complicated. Good. So when we say that no one is, as I mentioned, there is no strategy profile S prime that dominates this. But here no means this strategy profile S prime mixed or pure. We can say that we should say no mixed or pure strategy that can dominate. Good. Now, let's go about the for now about the this pure one. Okay, so let's see what do we do essentially. We will go and we will find among all pure ones, say that for the first player is the maximum, correct? So it means that no one can dominate this one, correct? So no one can dominate this 5 guy because that's the maximum by definition. All right, and note that here, we said that at least for one guy should be greater. So greater than or equal, it should be fine. So in that case, no one can dominate the 5 guys. Then we will go among the others for the second player. So we know that any other person in this game, it will be less than or equal to this. So the others, they cannot dominate it. The other cells that they don't have this 5 as the maximum. Maybe there are more. Here it is only one, but it might be the case that more than one cell. Then no one else can dominate it. Only those guys that are 5. Now among 5, we will go to the second player. Second player among we are choosing the maximum. No one among those maximum, no one else can dominate this person. And so on and so forth. So that's the idea that essentially shows that among pure strategies, no one can dominate this strategy profile that we will find that. Is it clear so far? Does it make sense? Yeah.
So like no one can get a higher score than or utility than
Exactly.
Okay.
And then, that's the definition. You see, we will say that one is dominating is in every aspect is better. And we want to say that no, I mean, you can, the final one that we will find, there is no one that in every aspect is better, and even in one of them is strictly better. Good. So that's the thing. But so far among these tables we are talking about, but what about mixed strategies? The mixed strategies, this is the problem. Mixed strategies can be huge. Here we have what is the number of pure strategy profiles? Just cells of this matrix. So if we have, say, if we have n players and k actions each, how many cells do we have here? Yeah. So n times k, k to the n. Any other answer? How many people say nk? How many people say k to the n? K to the n is indeed the answer, because each of them can take, like you can write it down. This is the way that you can see that. So you see, it writes this one. So for this guy, how many actions I can take it for the first person? I can take k answers. What about for the second one? I have k answers. What about for the third one? I have k answers, and so on and so forth. How many people I have it? N person. So it means that k times k times k times k. How many times k to the n? So k to the n is large. So if two actions n per layer would be 2 to the n is large. But it's still something that there is a finite number of them. For mixed strategies, they can be infinite, because you can put any probabilities here. As long as each of them is just a probability distribution, you will put it, and there are infinite number of them essentially. Good. Now I need to say that among those infinite guys, no one can dominate this guy. Good. So at least here I could see what I'm talking about. What about those other guys, these infinite guys? So what is the fact that I want to use now? And we are using that fact a lot. The GPA paradox, I will say. That your GPA, if all your grade is 45, your GPA cannot be 50. And vice versa. If all your grades are above 50, your GPA cannot be 45. So this is the same thing that I'm using here. What do I say? Instead that, okay, this guy, this 5 guy, here was the maximum. Good. What is a pure strategy in some sense? What are the mixed things? The mixed person is essentially some kind of probability distribution, very similar to that average about the GPA that I have mentioned. Every other mix, if you consider any mixed strategies of these guys, in some sense, what do? You are taking the average of some numbers, the first guy essentially. If you take the average of any of these things, if everyone is less than 5, the average cannot be more than 5. Good. Because you are doing exactly the same thing. You are taking the average of this guy. So you may get 5, you may get 3, because you put a different probability. So you may put it, I don't know, 0.2 here and 0.8 here, for example. That would be a mixed strategy. You will take C with this one and D this one. But anyhow, if 0.8 times 3 plus 5 times 0.2, it cannot be more than 5. It's exactly the same GPA paradox that I have defined. So you know that among mixed strategies, also the first guy cannot be, you cannot have a utility greater than. Then you will repeat these games now among those guys. And of course, if you are, the only way get to 5, note that if somebody wants to dominate, everything should be greater than 1. So if in the first guy, it is less than 5, it doesn't matter then what will happen after that. This guy cannot dominate this guy. So I'm fine essentially. To dominate it, I need to have the first component at least 5. If that does not happen, then I don't care about the others. Again, it's not a perfect thing. This is just something. It's not a stupid, essentially, strategy. So then I'm considering only I need to consider among 5 guys. That's the only one that can possibly be something that dominates this. Again, now everything is 5. The first component should be 5. Even 1 is less than 5, that cannot beat essentially this, and I'm fine. Now, among them, again, among all mixed strategies that the first component is 5, you will do the same action for the second player. Again, any mixed strategies of them cannot be more than this number that I'm selecting, because that's the maximum that I'm selecting. Good? Yeah.
Let's say Roger strategies you have to see that each player has the same number of keys. Like if one player, like let's say my top player had 3 strategies versus 3 actions versus my bottom player, just 2 actions.
Yeah, exactly. So here I assume K is the maximum. If K is the maximum, then it would be K to the. K is the maximum. At most, this one, yeah. If all of them are equal, essentially. Yeah.
So the strategy is basically you take the top of the distribution for mixed, right?
Yes, but I mean, that is very vague, essentially. How can I define that? In some sense, I will obtain this one by just taking the pure ones. That is one notion that you will get a top in some sense. And again, this top is not top. Top in, like, essentially, top means that there is no one can dominate it. It's not necessarily the top. Maybe everything is, like, maybe it's not good. But that is for one, it's not the case that it's completely dominated.
It doesn't matter how unlikely that probability is.
Yeah, exactly. So, I mean, note that unlikely probability is defined according to a strategy. So here, nobody is giving the strategies to me. The player decides about it. So here, when we talk about this kind of Pareto optimal things, essentially, everything is the thing that the player decides. So when we are coming to this game, in some sense, every cell has the same probability or the same likelihood, because the player decides which one want to go there. Nobody gives us the probability beforehand. So this is important again. When we consider this normal form game, it is not the case that it might be this one is more likely than the others. At this point, everything is the same. Players decide which one has the more likelihood that we will end up there. And that is part of the game. Nothing beforehand is given. Good. Good. So let's go here. So we talk about this one. There is another one which is also simpler, maybe simpler than this one, and at least more efficient in terms of running time. Here, if we have K players, what is the running time? This is a computational game theory. So what is the running time? So we need to go through the whole, this is at least a naive one. You may think about a better way. But you will go through the whole K to the N things, find the one that has the maximum. Maybe again, this maximum for the first player is 5 everywhere. Then you need to go again the whole matrix to find for the second player and so on and so forth. So the running time potentially can be N times. So the running time potentially can be N times K to the. Maybe times k as well, because you need to go through the strategy. Is there any like a bit more efficient? I mean, you can think about how you can do it more efficiently, but is there any other way that we can do that? This is like this is another one that I found one of them, correct? Again, there might be lots of them essentially. This is only among the pure ones. Even mixed ones can be many, many more, maybe infinite number of them. However, this was the one thing that you need to do this iteration or iterative algorithm. Can I find a better thing? Yeah, I will say this one. Consider a pure strategy with the maximum sum of payoffs. So the previous one, as I mentioned, it was n times k to the n, I think times k actually, because you need to at least go through the payoff of this guy, maybe k or something. This one, I will just, it is only k to the n, or actually maybe k times k to the n, because you need to sum it up. You will go to the cells of this matrix. For each cell, see what is the sum of the payoffs. All, just sum over all, guys. The one that has the maximum, just choose that. Clear? This one is also a Pareto optimal. But that this in terms of algorithm is simple, but proof is a bit more. I mean, you can actually use the same concept that I have mentioned, especially that GPA paradox. That again just play the same thing, and you can see why we have this property. That's an exercise. But that is a more efficient version. So is it clear the algorithm? So let's go and see an example here. I think. Good. So let's consider this game. So this is the prisoner's dilemma. Good. So here, let's see what are the Pareto optimal, guys. So DC is the Pareto optimal. This is this one. Why? Because this 5 guy is the maximum guy. Correct? This CD is also a Pareto optimal, because then we can go with any arbitrary order of players. Here, for this guy is the maximum. Good. What about CC? That is also a Pareto optimal. Why? Because of the second theorem that I have mentioned. Some of them is 6, 3 plus 3. That is exactly the one. You will go there among all of them. 3 plus 3 is 6. It is greater than anything else. This is a Pareto optimal. The only one that is not Pareto optimal actually is this one guy. Good. I will mention next time the concept of Nash equilibrium. It turns out actually all these guys that I mentioned, these are all Pareto optimal. In some sense, these are some good solution concepts. But this one, unfortunately, was not Pareto optimal. It turns out that's actually the only Nash equilibrium in this game. So in some sense, what's the meaning of that? It means that it depends to which solution concept you define. You may have a different settlement. There is no one that is the best. You define, okay, my settlement is this. I will be happy if it is like that. Then you will find some solutions for that. Again, why? Because there is, in this case, there is no single objective function, because there are multiple players. Each of them have their own objective functions. So with that one solution concept, that's actually the good solution. But with this one is the only Nash one that we are talking about. Now let's go for the other one. Which side of the road? I have left or right are Pareto optimal. Why? Because this is 1 plus 1, which is 2, and this is 2. Of course, you can use the other algorithm and do that. So in the common payoff games, we know that all Pareto optimal strategies have the same payoff. That is by definition, because these are common payoffs. Whenever it is like for any things, like you see here, it's a common payoff. So it is both of them get 0, or both of them get So you only need to find so you will find the one strategy that, or one, like in the common payoff games, as I mentioned, because all of them have the same payoff in each things. So only the one that has the maximum payoff is actually the Pareto optimum. So that would be simple ones. You may have a bit more efficient way to find these things essentially. Good. So that's about essentially the concept of Pareto optimality. Next time we talk about Nash equilibrium, and we will continue on the Nash equilibrium and others. Nash equilibrium, this one is a bit, as I mentioned, is a bit more easier, like is an easier one comparing to Nash equilibrium. That is more complex in some sense, and more type of things is coming there. But this is one reasonable concept, and we have things, and the proof, also are reasonable. So that's the thing that we are talking. Good. So I think that we will continue next time with the Nash equilibrium.